Hello, everyone. We are going to learn 6.7 Stokes Theorem. So we learned from previously Green's theorem, right? So we use the Green's theorem for 2 dimension. So Stokes theorem is for higher dimension for Green's theorem. All right. Okay. So what we gonna learn in Stokes theorem. So there is a line integrals and surface integral and curve. And moreover, Stokes theorem, we can use that circulation and more physics, fluid machines, and electromagnetism, and also Stokes theorem, Stokes theorem to derive Faraday's law for involving electric fields. They said here. Okay, so here is Stokes theorem. All right. So let S be piecewise smooth. So S is 2-dimension surface in 3D space, right? Okay, they say they're smooth. So it does not have to be whole thing smooth. It's a piecewise, so some part is sharp, right? And oriented surface, that means direction for the normal vector on the surface with a boundary that's simple closed curve C. We know that what is looks like a simple closed curve C with a positive orientation. That means the direction goes the counterclockwise, right? And if we have a vector field F with a component function that have continuous partial derivative on open region containing S, then we have this is a line integral formula, right? So we had that from previously. Now we have, this is a Stokes theorem formula. So let's take a look. So we have S from the line integral, C. And then we are using curl vector field F. So we had this formula, which is the cross product of vector field, right? Okay. And then we have a dot product with ds. ds means here tiny area of the surface, of direction of the surface, normal. Yeah. And they said the orientation matters. So positive orientation or negative orientation. Yeah. Okay. So I mentioned that we have total amount of rotation of vector field across the surface S for this formula. Okay. All right. Let's do this example. So we want to calculate line integral by using Stokes theorem. All right. So we have a vector field xy, x squared plus y squared plus z squared yz. And is a boundary of parallelogram with what is 0, 0, 1, 0, 1, 0, 2, 1, negative 2, 2, 0, negative 1. Okay, so if we were using line integral, then we have to use this formula 4 times because there is parallelogram which has 4 paths, right? So it's better we are using Stokes theorem. Okay, so let's pick 3 points here. 0, 0, 1, 0, 1, 0, 2, 0, negative 1. Okay, so then let's say that z equal to the equation. So ax plus by plus c, right? Okay, so for the first triple pair. So we have a 0, 0, 1. Then this is XYZ, right? So Z equal to AX plus BY plus C. So Z equal to 1. Then X equal to 0, Y equal to 0, then C. Yeah? Okay, in that case, C equal to 1, right? Okay, for second one, so 0, 1, 0. Okay, so Z equal to 0, then X equal to 0, Y equal to 1, and C equal to 0, right? Then Y equal to, I'm sorry, B equal to, C equal to, sorry, Z equal to 0, C equal to 1, right? Okay. Sorry, C equal to 1, then Y equal to 1, right? Because we have X, Y, Z. Yeah. All right. Then we have a B equal to negative 1 then, right? Okay, the last one, we have a 2, 0, negative 1. Okay, so I need to write down. Z equal to negative 1 and X equal to 2 and Y equal to 0 and C equal to, hold on 1 second. B equal to negative 1, right? But yeah, it's a 0, Y equal to 0, right? I'm right, right? And C equal to 1, constant term. Okay, then what do you get? So we have negative 2 equal to 2a. So we have a equal to negative 1 there, right? All right. Then we have equation z equal to negative x plus negative b is negative. So negative b is negative. Why? 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 Yeah, why? Plus 1. Constant term is C, right? Then we can rewrite this one z equal to 1 minus x minus y, right? Okay, the Stokes theorem said that we have double integral of S piecewise smooth oriented surface, right? Boundary. Yeah. So curl of F, dot product of DS, right? So we have then curl of F, dot product of DS. Okay. So how do you do? So this one, let me write down. So this one we have from previously, the cross product with the vector field, right? Okay, so that means we have I, J, K, then we have this formula. So if we don't remember, then the vector field has P, Q, R, right? The function or the equation, right? Or component, right? Okay, so we're writing P, Q, R. So if we don't remember the formula, it's easily to apply this one, right? Cross product. Okay, so we can do that. P, Q, R in that case. This is a P, this is a Q. So X, Y, And second component, Q, R, right? But then it's better using formula, more simpler. Okay, so let me write down, or we can use that. I'm gonna just writing the formula, right? PZ minus that. We know how to apply, right? Okay, let's do it. So we're looking at, where is it? Let me bring. So we're looking at the vector field. It's a function or it's a component. All right, so we're looking at R, and with the partial derivative with respect to Y, then Z is constant, so we keep that, right? Z. And second term, we're looking at the Q, partial derivative with respect to Z, so 2Z minus 2Z. I have, and we're looking at the P, partial derivative with respect to Z is 0. And looking at the P again, partial derivative with respect to, is it P or, hold on 1 second. Okay, made a mistake there. So this is R. And then respect to partial derivative with respect to X. Yeah, so let me rewrite. Okay, so let's take a look again. R, we're looking at R component, partial derivative with respect to X. There's nothing, it's 0. So 0 minus 0, which is 0, J. Now we're looking at the Q, partial derivative with respect to X, which is 2X. And we're looking at the P, partial derivative with respect to Y, then X, yeah? X is constant, so minus X. Okay, all right, so we have negative Z I hat plus X K hat, right? So we can rewrite this one as a component. So that will be negative Z 0 X. Yeah. All right. Now what we do, let's find out limit first. After that, we are looking for tangent vector. Yeah. All right. So let's find out limit. So we have the point from parallelogram, right? Okay. So we had triple pairs. Yeah. Sounds a little bit weird. Okay, so we had a 0, 0, 1, 0, 1, 0, 2, 1, negative 2, 2, 0, negative 1. And then we had the equation, right? So z equal to 1 minus x minus y, right? So we took the only x, y. So those point in the xy plane. Yeah. Okay. Then either one, it's okay. We can pick dy dx first, second, or dx dy. It's okay. Let me follow the book. So x equal to 0 to 1 because x 2. x, yeah? The upper bound is 2. And y equal to 0, 2. Sorry, crazy. Forgive me. So y equal to 0, 2. So upper bound is 1. Right? Okay, so we have a curl of vector field F, and then we make a parameterization xy, right? And then we have to have a cross product of tangent vector respect to x and y, right? So we had that. Tangent vector respect to x, cross product of tangent vector respect to y. And then dx, dy, right? I'm sorry, dy, dx. Sorry about that, dy, dx. Okay, now, so we had earlier cross product of del with vector fields. We had a negative z, 0, x, right? Which is curl of f, right? But then we have to make a parameterization with that, right? So let's do it. Let x, y equal to x, y, z. But then z, we have x, y, z equal to this equation, 1 minus x minus y. Okay. Now, let's looking at this one. And then we want to find out tangent vector respect to x. Okay. So we're looking at this one. And then partial derivative with respect to x. Then we have 1, 0, negative 1. Yeah? All right. So there will be 1, 0, negative 1. And we're looking at the y, partial derivative with respect to y, right? So 0, 0, 1, negative 1. Yeah? Okay. 0, 1, negative 1. Okay, so we have two cross product of tangent vector, right? So let's do that. A lot of work. But it's less than that line integral work. Okay, so let's do this. Cross product. E, J, K. All right, so 1, 0, negative 1, 0, 1, negative 1. Okay, so we're looking at the I minus J plus K. So we get this 0 plus 1, right? 0 plus 1. Looking at the J, so here, so negative 1, and then rest is 0, right? So negative 1. And K, looking at this, everything is 0, right? No, K. So we have 1 as well. So this is 1. All right, then we get I plus J and K. Yeah. Plus K. which is we can use as a component expression. So 1, 1, 1. Yeah. Okay. So let's do it. Let me. Ooh. So that. Let me do one more time. Okay. Now. What did we have? We had curl of f. We had earlier. Where you go? Too much. We had a negative z, 0, x. Yeah. But then what was the z? We had 1 minus negative, oh, you cannot see. So what was the z? Z is negative 1 minus x, y, right? Okay, then just distribute the sign, then we get negative 1 plus x plus y, right? And then x, sorry, 0x dot product with 1, 1, 1. Yeah? You guys okay? All right, so maybe we can see that there will be, oh, maybe next time. Like that. All right, so there will be from x equal to 0 to 2, y equal to 0 to 1. What was it? Positive 1, negative 1. Negative 1 plus x plus y, 0x. And dot product with 1, 1, 1. Yeah. Okay. Now, dy dx. So what do you get? X equal to 0 to 2. Y equal to 0 to 1. We multiply first component with the first component and second component with the second component, and third with the third, right? So we get negative 1 plus x plus y and add, yeah? And dy dx. Okay, so there will be x equal to 0 to 2. We have a y equal to 0 to 1. So we have a 2x plus y minus 1 dy dx. Yeah. Okay, so we get 0 to 2, y equal to 0 to. Okay, now let's integrate respect to y, right? So we have a 2xy plus y squared over 2 minus y, yeah? And then evaluate from 0 to 1. So we have 2x, 1 plus 1/2 minus 1. And everything is 0. Okay, so there will be 2x. And we get the negative 1/2. All right, now integrate with respect to x. So we have a 2x squared over 2 minus 1/2 x. And then we evaluate from 0 to 2. So we have 2 squared minus 1/2 times 2 So we get 3. Yeah. Very good. Okay, so we have a verifying Stokes theorem for a specific case. So we have a vector field and surface S, where S is a paraboloid, z equal to 4 minus x squared minus y squared. And then this surface is outward orientated, or not orientated, oriented, and z equal to greater or equal to 0. Yeah, positive for the z. Okay, so outward oriented means no more points upward, means that away from, instead of ball. So there is a oriented outward. Yeah, we can say that, right? Okay, so we have a Stokes theorem formula, right? We are using that, and then we're gonna show the line integral, whether we get the same answer or not. Okay, so we have a double integral of the S, right? And then, oops, the curl of vector field F, and then dot product with the ds, yeah? So that is surface integral of the curl, right? Okay, so, ooh, screw up, right? Let me bring this in here. Okay, now I wrote down the formula again here. Okay, so we had a curl of a vector field F. We have a not dot product, cross product of del and the vector field, right? So if we don't remember, we can just rewrite everything. This is easily to remember, right? We can apply the formula, but since we can use the formula, right? So we can just apply directly. This is more easier, right? Okay, so let's do this one. So we have, looking at the R, this is PQR, right? PQR. Okay, looking at the R, and then partial derivative with respect to y. So there is no y, so it's 0. And then we're looking at the Q, partial derivative with respect to z, so which is 2. And looking at the P, partial derivative with respect to z, 0. Looking at the R, partial derivative with respect to x, 2x. And looking at the Q, partial derivative with respect to x, no x, 0. And looking at the P, partial derivative with respect to y, it's 1, right? Okay. So we can see the negative 2i plus negative 2x j minus k, yeah? So there will be negative 2, negative 2x, negative 1. Okay, now, all right, so let's make a parameterization. So this is just general. General is always easier. So let's make r over xy equal to xyz there. Then we can express this one as xy, then z, we have equation, which is 4 minus x squared minus y squared. So 4 minus x squared minus y squared. Okay, let's find out the tangent vector, right? So tangent vector of x. Then we get, we're looking at this one, partial derivative with respect to x. Then we get 1, 0, negative 2. And how about partial derivative with respect to y? Then 0, 1, -2, right? Okay, let's make a cross product of two tangent vectors. Then we get ijk. Then we have 1, 0, -2, 0, 1, -2. All right, so there will be I minus j plus k. So we get that 0 plus 2, right? And j, we get positive 2 minus 0, right? So positive 2. And k, we get 1, right? All right. So there will be 2 2i hat minus 2j hat. We get the minus. Let me double check. So j minus minus minus, yeah. So we get negative. So we get the positive, right? And then plus k, right? So if we express as a component, that will be 2, 2, 1, right? So 2, 2, 1. Oh my gosh, sorry about that. We have negative 2x, negative 2y, right? Or you get the negative 2x, 2y. So let's see. Do one more time. So partial derivative with respect to x. So x minus 2x. So x 1, 0 minus 2x. Yeah. Oh my gosh. So dumb, right? And then partial derivative with respect to y, 0, 1, -2y. Yeah. Sorry about that. So negative 2x and -2y. So so we get 0 positive 2x, yeah, positive 2x. So we have 2x, and then j, so positive negative y, right? Yeah, so that would be y, and then rest is okay, right? Okay, now we have a 2x, 2y, 1. Then let's go back to the formula, right? So there will be, let me make a little bit special for this one. All right, so we will get the surface integral, so curl of vector field dot product with ds. That will be changed to region D, curl of vector f of x, y, and dot product with tangent vector x cross product with y, dA. Yeah. All right. Okay, so there will be so we have x, y, z, right? So x, y, z. So we will get, we're using this one. And then we are using this one. Yeah, dot product. So there will be -2, -2x minus 1, dot product with 2x, 2y, 1. dA. Yeah, so there will be, okay, let's simplify first, then we check the limit, right? So negative 4x plus minus and negative 4xy and minus 1, right? dA. Okay, so let's talk about for limits. So we had the equation z equal to 4 minus x squared minus y squared. Okay, then if z equal to 0, because z is greater than or equal to 0, right? So we can rewrite this one is x squared plus y squared equal to 4, or we can say that greater or equal to 4, right? Okay, then let me write down since z is greater or equal to that, we have that, right? So what's the z equal to 4 minus x squared minus y squared? Okay, then we solve for y. Then we have y equal to plus minus square root of 4 minus x squared. Okay, then in that case, if y equal to 0, then x equal to plus minus 2. Yeah. Okay, so then let's make a limit like that. So we will have x equal to negative 2 to positive 2. Then y equal to negative 4 minus x squared. And then y equal to positive 4 minus x squared, right? Okay, then we have a negative 4x minus a 4xy minus 1 dy dx. Then let's integrate respect to y. So we have x equal to negative 2 to 2, then negative 4xy minus 4xy to the second power over 2 minus y, right? And then we want to evaluate from negative 4 minus x squared, y equal to 4 minus x squared, okay, dx. All right, so that will be x equal to negative 2 to 2, negative 4x, whew, square root of 4 minus x squared minus 2x square root of 4 minus x squared minus, okay, square root of 4 minus x squared. Yeah. Okay, minus, okay, let me writing out, okay? Okay, so I wrote down everything. This one is 4 minus x squared, right? So this one also 4 minus x squared. So let's see which one we can combining like term. All right, so but luckily, let's see. So luckily we get this is a negative, this is a negative, this is a positive. So this is 0, right? We can simplify. This is 0. All right, then we have negative 4x and then multiply. So we have a negative, negative, right? Which is negative. So we have a negative 8x of square root of 4 minus x squared, right? Okay, so there will be x equal to 2, negative 8x square root of 4 minus x squared. Okay, let's take a look at this one. We have a negative 1, right? negative, 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 which is negative. So negative 1. So negative 2 of this. Yeah. So there will be negative 2 square root of 4 minus x squared dx. Okay. So, okay. So let's do that. Evaluate, right? When x equal to 2, oh no, integrate first, right? So look, we have to recognize, right? So we can integrate this one, but we cannot integrate this one because we have axis inside. We have to have a channel to get that, right? So let's just separate term by term. So we have x equal to negative 2, 2, 2. And then let's take out the constant outside, negative 8, right? And then x square root of 4 minus x squared minus 2. And then x equal to negative 2, 2, 2. And the square root of 4 minus x squared dx. Yeah? Okay. Let me change it to 1/2 power. Yeah? So that we can integrate easily. So there will be, we have 4 minus x squared, 1/2. Okay, we have to have a channel, right? So negative, if we derivative inside, we have to have a negative 2x here. So negative 2x, okay, negative 2x, and then we divide by negative 2x, yeah. If you're not familiar with this one, please watch this method in the calculus 1, or use substitution, right? So use sub, let u equal to 4 minus x squared, derivative, we have negative 2x, yeah? And so on. You can do that. All right, so then we have positive 4. And then integrate. Then we have 4 minus x squared and 3 over 2 and 2/3, right? From evaluate that, right? Okay, let's take a look quickly. We evaluate when x equal to 2 or negative 2, what do you get? We get 0, yeah? So this one is 0. Okay, let's take a look the second term, right? So second term is hard to integrate, right? Because we have to have a chain rule. So we have to have negative x here. Yeah. So at least we have x. Negative 1 we can input there. Negative 1 there, negative 1 there, right? But then we cannot input x. Yeah. So we cannot do that. So what do you do? Just using logic here, more faster. Okay, so we knew that ooh, this is upper semicircle, right? Semicircle, upper half, semicircle. Note. Half a circle, half a circle. Okay, then how do you find the area? So there will be pi r squared, but then it's a half divided by 2. So we have radius equal to 2, right? So pi 2 squared over 2, which is 2 pi. Okay, then we get negative 2. So we will get negative 2 and 2 pi, which is negative 4 pi. Yeah. Okay, then what is the negative means? It's opposite direction, right? So we have opposite direction. And then in the beginning, they say the outward surface, right? Surface is the outward direction, right? So let me see. We had outward oriented, right? So we can say the inward then. Okay, so let's talk about the line integral so that we can verify the Stokes theorem, whether we get the same answer or not, right? All right. Okay, so let's make a parameterization. So we have r of t equal to x, y, z. Then we notice that x equal to r cosine t and r sine t and z. Yeah. Okay, then r in that case, the radius equal to 2 because we have 4 minus x squared y squared, right? So we had earlier x squared plus y squared equal to 4. So r equal to 2. So 2 cosine t and 2 sine t. Let's make a z equal to 0 since z is greater than or equal to 0. The smallest one is 0. Yeah. So let's make a smallest one. Okay. Now what we are doing, t is between 0 and 2 pi because it's a circle, right? So, and t is between 0 to 2 pi. Okay, let's apply the formula. Okay, so I wrote down the formula here. So we have the path, right? And then vector field dot product with dr equal to from 0 to 2 pi, t is between 0 to 2 pi, and then we insert the parameterization inside the vector field, and then dot product with the r prime of t dt, right? Okay, so we have x to z x squared from the example earlier. We want to insert r prime of t. Yeah. So we have y, which is 2 sine t, and we have 2z, which is 0. Now we have x squared, so this is 2 cosine t squared. You may write down everything? So let's do it. So we have 0 to 2 pi and x, y, z. We know that, right? Okay. So insert r of t into the y. So it's a 2 sine t and 2z 0 x squared. So 2 cosine t squared, right? Okay. R prime of t, what do you get? So we have 2 cosine t, derivative of 2 cosine t is negative 2 sine t, and derivative of 2 sine t, which is positive 2 cosine t and 0, right? Okay. Then 0. dt. All right, so we do component with a component for cosine squared t. Okay, let's do that. 2 sine t times negative 2 sine t, which is negative 4 sine squared t plus 0 and 0. Oh, okay. Right, so dt. So we have from 0 to 2 pi, negative 4 sine squared t. So we have to integrate. Yes. All right. So let's do this one. Trick, yeah? All right. So we can like integrate, right? Sine squared t. So we have to convert to the trig identity, right? All right. So there will be, let's take out the negative 4 from 0 to 2 pi sine squared t, which is we can have 1 minus cosine 2t over 2 dt. Then we do integrate term by term. So we have a negative 4 outside. And then 1/2. How do we integrate? So 1/2 t and minus cosine 2t. How do we integrate? Sine, right? Sine 2t, negative sine 2t. But then we have a 2, so we have to make 1/2, yeah? Okay, so we do integrate the evaluate from 0 to 2 pi. So there will be negative 4, 1/2, 2 pi, minus 1/2 sine 2 times 2 pi, minus 1/2 0, sine 0, 0. Okay, good. We don't have to do this. All right. Then, let's do this one. This one also 0, right? Sine 4 pi. And then 2 with 2, we get negative 4 pi. Let's use that, yeah? So then since line integral, same as what we had Stokes theorem, right? Okay, so we verify that Stokes theorem. Yes? Yay. Okay, let's do next one. Okay, so last concept for this section. So in the electric fields, the curl of electric fields can be interpreted as the negative of the rate of change of the corresponding magnetic field with respect to time. Yeah. Okay. So curl of electric field. Then we have a negative of the. We are looking at the vector field about the magnetic field, and then partial derivative with respect to t, right? So we called this one is Faraday's Faraday's law. Yeah. Okay. So let's do this example. So we want to calculate the curl of electric field E. So they're using just the first letter E from the electric field, and corresponding magnetic field is constant field. So we have a constant, right? Okay, so the formula said that we have negative of partial derivative with respect to t, right? Okay, but then we see that everything is constant. What do you get then? Yes, we get 0, yeah? So we're looking at B, magnetic field, and then partial derivative with respect to t, then we get 0, 0, 0. But then formula say that we have a negative. So basically what this mean, right? So this means the cross product of del, and then vector field E, right? So electric field, right? And then we have negative, still we get the 0. So what this means, if we get the curl of vector field is 0, then that means there is no curl, right? So then they say that there is no rotational. Yeah. Okay, let me write down everything. Okay, so I wrote down what I said earlier. So there, yeah. And then thus the electric field has no curl because we get the 0 and 0 vector. And this means no rotational because curl is 0, means no rotational. And then the rotational, we said in one word. And let's take a look in the bottom. So what can we notice that, right? So a consequence of Faraday's law is that the curl of the electric field corresponding to constant magnetic field is always 0. Yeah. Okay. Thank you for watching. I will see you next section. Next section is the last section. All right. Thank you. Bye.